Good afternoon, everybody, and welcome to another one of our world famous at this point speaker series. Today we have Dr. Eric Evans, who is the director of MIT Lincoln Laboratory, which is a multidisciplinary, federally funded research and development center run by the Massachusetts Institute of Technology for the Department of Defense. As director, he's responsible for the laboratory's strategic direction and the overall technical and administrative options. Ladies and gentlemen, Dr. Eric Evans, how are you today?
I'm fine, Chuck. Thank you. And hi, everybody. Thank you for connecting. And I'm going to go through some charts to describe what Lincoln Laboratory does. And then we'll have some time at the end where I can answer any questions you might have. But first, I wanted to show you a picture from a long, long time ago. So
All right.
This is a picture of me when I received my Eagle Scout Award back in 1977. I was in Troop 273 in Stowe, Ohio, and I went to Philmont and hiking in the Grand Tetons and canoeing up in Wisconsin with our scout troop. And I learned a lot about leadership as a scout, and a lot of what I do now is really based on what I learned in scouting. So what you're learning in scouting is a great way to learn how to do leadership later on in whatever you do in your careers. And after high school, I went to Ohio State and I got a bachelor's and a master's and a PhD degree in electrical engineering. And I worked at Battelle, which is in Columbus, Ohio for a while. And then I went out to New England to work for MIT at Lincoln Laboratory, and I've been there for about 30 years. And it's really been a great place to work. And I wanted to show you a couple of pictures. So these are two pictures. The one on the left is the front door, and you can see some antenna dishes to the left-hand side of the picture. And on the right-hand side, there's a photo of our microelectronics laboratory. We make computer chips and advanced focal planes and a whole range of interesting electronic devices in there. And we do work for the Department of Defense and the Federal Aviation Administration and NASA and the Department of Homeland Security and lots of other organizations. We develop technology to try to protect the United States, and we do mainly research and development. So our role is to create the first copy of something, the first copy of a new idea, something that might be very high risk or high payoff. And then if what we do works, then we pass what we do to industry like Lockheed Martin or Raytheon or other companies, and then they'll create many copies of it for people to use. And right now we have about $1 billion in funding, and we have about 4,000 employees. So it's a very big place, and there's a lot going on at any given time. So on this chart, I just show a whole range of areas that we're working in. Some of them are more in what we call technology areas. We make new lasers, we make new focal planes, so your cell phones or cameras that you might have electronic focal planes in them. So we make those with a lot of pixels, and they're very sensitive, and they go into systems in satellites in space or in aircraft. We develop chips that can count individual photons. So if one photon of light comes back from something, we can see it and count it and do something with that. We create new systems to develop what's called quantum bits for doing quantum computing. And we're trying to create the world's first quantum computer at Lincoln Laboratory. And then we do a lot of electronics work at a very small scale. And then on the right-hand side of the chart, we take these technologies and we try to build these big system prototypes. And these are things like new telescopes for looking deep into space, new radar systems, new sensors that might go on satellites. We're doing what's called laser communication in space. I'll show you a little bit more about that in a minute. And then we create new rockets that are targets for certain systems out there. So these are like big Estes rockets in a sense. Some of them can fly even thousands of miles, and we create versions of those that can be used for the Department of Defense to help find ways to protect our country. So there's a whole range of interesting work like that. And I'm going to talk a little bit about radar, and I thought I would go through and describe what radar is. So radar stands for radio detection and ranging. And on the left-hand side of this view graph, there's a an antenna, which looks like a big dish, and there's a point on it towards the right-hand side of it, and that's where the radio waves come out, and they reflect off that big dish, and then they get pushed off toward the right-hand side of the chart. So that's a wave going off, and then it reflects off an aircraft or something up there and comes back and then is received by the radar dish. And if it takes a long time for the radio wave to come back, the target is far away. If it takes a short time, the target's pretty close. And then you can figure out what angle it's at by steering the dish and seeing different things. And the radio waves travel at the speed of light, so you get all that information very, very fast. And that's how a radar works. And then the antennas work just like a flashlight in a sense. So on the right-hand side of this chart, I have a picture of a radar dish antenna called, this radar is called Altair, and it's out at Kwajalein. This is an island halfway between Hawaii and Australia in the middle of the Pacific Ocean. And that dish is about 150 feet across. So radio waves come out of that pointy end of the antenna toward the right-hand side, and they reflect off the dish and go off in a direction much like with a flashlight. You have a light bulb that emits light like radio waves, and it reflects off the reflector in the flashlight and then goes off into a direction, in this case, into the right-hand side. So this is how antennas work, and we do a lot of work with antennas and radars in this way. And this chart shows a new radar system called Haystack, which is in Westford, Massachusetts. And this is a giant radar with a lot of power. And what we use this for is we look deep into space for things that might be intending to do harm to our satellites. And we're very worried about that right now. Satellites like GPS or communication satellites and things like that. And so this is a really big radar. It's got a big antenna dish inside, and it's got a transmitter that's really, really powerful. And we were asked by the Air Force to upgrade this radar to work at a very high frequency so that we could see really, really small satellites. And to do that, we had to put a new antenna dish on it, and we had to put a new transmitter. That's what creates the radio waves. And to do that, we had to bring in this giant crane. So the picture on the right-hand side shows a crane. That crane is 400 feet tall. Wow. There are only 6 cranes like this in the country. And it took 65 semis to bring this crane out to the site. And then it took a crane to build the crane. And with that, we took that big ball shape, which is protecting the antenna. That's called a radome. We had to divide that into pieces and take the top off. And we had to take off the old antenna, which didn't work at the high frequency that we wanted to use, and put on a new antenna that did work at that high frequency, and put a new transmitter and everything. And then we put the cap back on and reskinned it, and we only got struck by 1 lightning bolt on that crane. But it works great now. So every day, this radar looks out into space and looks around all of our satellites up there to make sure that bad things aren't happening. And it's helping the U.S. to protect all the expensive satellites and important satellites that we have up there. And so this is an example of a big radar project that Lincoln Laboratory led. And right now it's a part of what's called space control or space protection. And there is no other radar like this in the world. This is the best radar, the highest frequency, the highest power ever built. And then on this view graph, I show another kind of radar that's on an aircraft, and this is called an E-2C. This is an aircraft that takes off from an aircraft carrier, and it flies over a carrier battle group to look around to see if there are missiles coming or other aircraft coming, and it's used to protect the fleet. And it has a radar that's at the top part of the aircraft that looks like a little dish, that plate shape. And we were asked by the Navy to find ways to make the radar work better. So what was happening is when this airplane was going near land, there were reflections from mountains or towers or buildings that were coming into the antenna and interfering with some of the small targets it was looking for. So we came up with a new technique that's called space-time adaptive processing. And what that allowed us to do is to make the radar listen to the environment first to figure out all the interference that was coming in. And then we could adapt the antenna to remove all that interference before it would look for small targets. And that made it work very, very well in a very difficult environment where there might be a lot of interferers or even what we call jammers. And to make that work, we needed to build new antennas, new receivers to detect the radio waves, and a new computer to do some of the processing. And on the upper right-hand side of this chart is a prototype that we built out in Hawaii. And you can see the antenna at the top of that tower and some trailers with the equipment that we were using to test it. And I spent some time out at Hawaii making this radar work. This was a lot of fun. So I was out at Hawaii for about a month working on this. And this is at the edge of a cliff. So there's about a 1,700-foot drop from the edge of that island there down to the water. So it's airborne enough. And we could represent an E2 flying around by having a test bed that was on the high up in a mountain on the island of Kauai. The reason I go through all that with you all is almost all engineering projects are a little bit like that. You come up with an idea for something that you can try. Maybe it works well, maybe it doesn't. If it doesn't work, you try to learn from that, and you try again and again and again. And if you ask any scientist or an engineer about things that they've been developing, they'll probably have many, many failure stories that they can tell you. But the idea is to learn from the failures and then try to do better the next time. So I wanted to show you another project we've worked on to do laser communication in space. And this is for a satellite that was put in orbit around the moon. And what it shows is the probe that was launched in the upper left-hand side, and that little gold ear on the side, on the right-hand side, is a laser communication link that we prototyped. And at the figure below that is a ground terminal that has some telescopes in it to collect the laser energy coming from the probe. And one of the innovations in that is what's called a superconducting nanowire array, so it can detect single photons of light. So if one photon of light comes down, we can detect that and get information. And this was launched around the moon a few years ago, and we were able to demonstrate about 600 megabits per second from the moon down to the Earth on half a watt of laser power. So really amazing capability. And this type of technology will be used with future probes out to Mars and Jupiter and beyond. And then just a couple more charts. So we also do radar work at very high frequencies that include light, and we call that a LADAR. And we built LADAR systems that go on aircraft. There's an aircraft shown in the upper left-hand side of this chart, and the LADAR is below that picture. And I don't know whether you'll be able to see this clearly. It's a movie, but if we can send light energy into a forest, if the light goes through the trees and reflects off the ground and comes back up again, we can get information in 3D of what's going on in a forest, and then look beneath the trees to see what we can find. And I'll show you, I'm going to run this, and you may be able to see it. So red is down low here, and some of the other colors are higher, and we're walking down a trail underneath the canopy. There's another trail, and you can see some of the trees, and we can walk through and look for things. And it looks like there's a wire up there, and then there's a tent. Wow. And then because we have all the three-dimensional information, we can then electronically take out all the trees and look down below, and we can see the encampment in the forest. You wouldn't normally be able to see this from an aircraft with a camera looking down. And so these are some of the technologies that we're developing for use for defense, but it's also good for using systems like this for archaeology, to look for ruins and things that might be in jungles. So that's another area that we're working. We're also developing satellites to look for planets in space, and this is a system called TESS, the Transiting Exoplanet Survey Satellite. It's got a very, very sensitive camera system on it. It's now in orbit around the Earth. It looks at stars. On the right-hand side of this picture, we have an image from TESS that has 200,000 stars in it. And it looks at each star, and if a planet transits in front of it, you can see the star get a little bit dimmer, a little bit brighter, and you can figure out how big the planet is and how far away it is away in the orbit, and learn things about planets and stars from far away. So we've worked with NASA Goddard and others to develop this probe. So just to wrap up, I wanted to mention, so careers in science and engineering are very interesting. And I've found over the years discovering or building something new is very, very exciting. And there are many failures along the way, but you learn from those and you do better. And then also, as scouts, you are learning much about leadership. It's very important. Things like having a plan or having a vision, learning how to communicate with others you're working with, and treating people with care and with respect. And those are very important lessons to learn. And you're learning it not by reading a book or by taking a course. You're learning it by doing it, within your troops or your packs. And it's a very important skill to learn. And if you have any questions about anything that I went through with Lincoln or anything at all, you can contact me at the email address shown here. Or if you'd like the charts, I can send those to you as well. So feel free to send me a note. So with that, I'll stop. And I think we have a few more minutes, but I'm happy to answer any questions you might have.
Great, thank you very much. Did you ever get discouraged after an experiment fails?
Yeah, it's discouraging. There are some times when multiple things break at once, and the key thing is to stay calm. And what usually happens is you get a group of 5 to 10 people together, and you kind of explore what the problems are, and together you figure out what to do next. And a lot of the innovation we do is a group effort, and it's very interesting to see how that works. And we all support each other for those down moments.
When you were working with the large crane and kind of seeing how you're going to replace the antenna on the inside and lift up the I'll call it a lid for lack of terminology onto the big dome, what kind of brainstorming ideas and techniques do you use when you're trying to solve all these problems or find new things?
Well, we usually try to come up with multiple options for doing something, a whole range of ideas, and then we do an analysis to figure out what might be best, and based on that, we'll try something, and then after we try it, we might find out that maybe that wasn't the best idea, and then we'll go and we'll try one of the other alternatives. So it's good to have a range of ideas because very often you have to jump to another one if your first idea doesn't work.
Similar to the scientific method, but more, test it out and see what happens.
Yep.
Yeah. All right. Did you always want to be in the field that you are in now, or was there something significant that just sparked your interest and steered you in this direction?
Well, I decided I wanted to be an engineer or a scientist in fifth grade, and I had a great teacher back then that really made it exciting. And and then when I went to college, I learned that I really enjoyed doing research and development work, and I was very fortunate to find a place like Lincoln Laboratory that did a lot of that. And so the motivation to work in this area kind of grew over time, but I started at an earlier age.
Okay, we have some questions. One question is from Scout Sebastian, who wanted to know how long does it take to start and finish some of these projects?
Oh, that's a great question. Some of these take 3 years, 4 years, maybe 5 years. And then we also have rapid development projects. Well, we might go from idea to building something in a matter of weeks to a few months. And so we have all scales for how quickly we have to work.
Here's another question from Matthew. How old do you have to be when you can work at Lincoln Lab?
Well, you should graduate from college. So I think the youngest employee we have right now is 21 years old. Um,
Okay.
so usually we have people that have graduated with a bachelor's or master's or PhD, and we usually hire right out of college, and then we grow them in different areas that are of interest to the projects we have and to them as well. Um, but if this kind of work looks interesting to you all, work hard and learn math and science, and but also learn how to write and learn how to communicate and speak in front of groups and everything, and you can have a very exciting career in science or engineering.
Eric would like to know, what was your favorite project and why?
So that project that I described with the E-2C aircraft, that was one of my favorite projects. That one was tough. And
That was
I
also the
mentioned,
Hawaii one.
yeah. So the Hawaii aspect was fun. And we used to sit at the edge of that cliff looking out, having lunch. We could see whales breaching off the coast. It was a beautiful day, almost every day. And I really enjoyed the technology in that project, but also, the people we were working with in the site we were at. But we learned a lot with that. I mentioned the one bad day with the Corvette with that project, but we probably had 50 bad days with that we had to work through problems. And then when we were done, it was just very satisfying to have something that was very unique and new come together and work. And I really enjoyed working on that.
You mentioned being interested in the field or going in this direction since 5th grade. So I guess the question is, was your Eagle Scout project in any way related to engineering or something along these lines?
It wasn't. So I built, working with others, a whole series of things that we needed in the church that was sponsoring our troop. So maybe that was engineering related to build those things, but that's.
How do you stay motivated when you go through these days where you might have to redo a bunch of things? Like, what would you consider a bad day? Like, how do you stay motivated?
Well, sometimes it's good just to take a break from what you're thinking about and think about something else. And then over time, the idea might come together better in your head, and later on, you come back and try again. But also, I mentioned that team sort of innovative experience. It's really amazing. I found how that works. How, something you hit a roadblock, you don't know what to do, and you sit in a room with a handful of very smart people and bounce ideas off each other, and then something comes together and eventually works. And so, taking breaks, talking with others, and just trying some things is really been the best way for us to work through some of this and get through those down moments.
Thank you. Alexander would like to know, do you implement any artificial intelligence at Lincoln Labs?
We do. We do a lot of artificial intelligence, and it's a very exciting area of research right now. So we take data from a whole range of sensors, and we use artificial intelligence to integrate it together in a way where we can find things that would overwhelm a human. So there are things that we look for that take a while to find, and if you had a human looking, they might get tired or they might miss things. But we can use algorithms to help find things, and then the algorithms will tell humans to look here. What do you think? And then they'll make decisions about what to do.
Tanner would like to know all right, so I think we already talked about what your hardest project was. Oh, here's another good question. Kelly would like to know, was your trip, the project that you had in Hawaii, was it very exciting and fun because you were in Hawaii or because of the project you were doing?
It was both, but but it was an especially exciting project. And I look back, I probably learned more working on that project than any other I've been on.
Is it difficult managing the laboratory with about 4,000 employees, or does the Department of Defense lend you a hand in management?
Well, we have excellent leaders at all levels working on these projects, and uh, what we do is the best way of running a lab like Lincoln is you get the best people you can find, and you turn them loose and stay out of their way. And as the director, you have to jump in every now and then to help with something, but great people working at the lab usually figure things out, and we're very fortunate to have a lot of very smart people, and I think for the people that work here, the thing they say they like most about working here is the great people that they get to work with.
What's the fun part of your workday and maybe the hardest part as a leader?
I think the most interesting part of what I do is to figure out what's next for a laboratory like Lincoln to take on. So there are a lot of threats out there, and they're changing pretty quickly. There are bio threats and missile threats and threats in space and threats underwater and a whole range of areas that we're worried about. And so we have to figure out how all that's changing and then try to stay ahead of that. So we ask the question, what technology should we be developing, or what systems should we be prototyping to be able to stay ahead of those threats so that the US has capability to defend against those and we're not surprised. And I find that kind of thinking very, very interesting. And then the next part of it is to really see the ideas come to life when we build something. But that's what I like doing the most. What I like doing the least is maybe traveling to DC, do that a fair amount, and it's important to do that. And there are messages to give, and you know, there are people we have to work with to try to get the right thing to happen. But I much rather be working with the whole range of people making some of these projects come to life than flying around.
All right, so you mentioned threats. Are there any projects that you're currently doing to help with the COVID situation? I'm considering that's a threat.
We are. So we have a group of people at the scale of about 200 now working in the bio area. And so we worry about defending the U.S. against biological threats with advanced sensing and ways of mitigating threats when they come up. And this particular pandemic issue we're involved in now, of course, is very, very serious, and we're developing ways of trying to move more quickly to address problems like this. And there's a whole group nationwide working on this. We're working very closely with them.
What would you say has been maybe the most dangerous project?
Uh,
I mean, that could go either way, maybe mechanically speaking, or risque for the DoD.
you mean dangerous that we've been involved in? Well,
Yes.
I've personally have been involved in projects where we're flying around in aircraft, doing certain things I can't mention, unclassified, or on ships doing certain things, and it can get pretty rough. I'll just mention I was on an aircraft one time doing something, and the flight was so rough, and I was knocked around so much that I couldn't have dinner that night. So that was that wasn't dangerous, but that was a rough day.
Do you have any advice you could give any of the young scouts who might want to follow in your career path, or any advice for them in general?
Well, I think one, by being in Scouts, you're learning a lot, as I mentioned, about how to be leaders. And it's important to learn how to do that, whatever you do. If you're interested in science or engineering, as I mentioned, you want to make sure you work hard in math and in science, but you also have to work hard in English and social studies and the other areas, because you have to understand how the world works and how people are and how to influence people with some of the ideas that you have. So it's all important. Uh, and then, you know, at some point, if you want to go into science or engineering, there are a lot of great schools across the country that you can apply to and work hard. And then there are a lot of great places to work after that. So there's such a need for science and engineering talent now nationwide. If you uh, get educated and get a degree in one of those areas, you will be highly sought when you come out. So it's a great career to go into, and I highly recommend it if you're interested.
All right, thank you very much. Ladies and gentlemen, this has been Dr. Eric Evans from the MIT Lincoln Labs. If you could all turn on your cameras real quick and give him a wave and say thank you very much, that'd be fantastic. They're all coming on.
Thank you.
Thank you, thank you.
Thank you.
Thank you.
Nice
Thank you.
nice to see you all.
This has
Thank
been
you.
great.
Thank you.
What?
Thank you.
Yeah.
Take care.
And